I am Devopratim Ghosh, and in today's demonstration we are going to see a practical angle for transmission lines. That is, for a given transmission line we shall try to measure its characteristic impedance, its attenuation constant and its phase constant for a given frequency. So what I am holding right now in my hand is one of the most easily available transmission lines, that is the coaxial cable. Now you can see at one end it has a small circular cross section that is called as a small coax, and on the other side you can see there is a big connector that is called the n-type coax. So this difference is there because we have to connect this line to this big instrument that you can see on the table. Now this big instrument is called as a vector network analyst. Now when I say network, it does not mean the computer network, it simply means an electrical network. So this network analyzer can give you all the network parameters of any two-port network. So this is port 1, this is port 2. But as far as transmission line measurements are concerned, we are going to consider ourselves or restrict ourselves to only one port. So therefore this n-type connector will be connected onto the port 1 connector. You need to securely fasten it. Now if you look very closely at the display, this display is in the form of a Smith chart. Now this is a big circle which shows you the R equal to 0 locus, and inside there are multiple more of the constant resistance and reactance circles. Now you can see a green colored line which essentially is indicating the impedance that is seen by port 1 at different frequencies. So for different frequencies it is seeing different kinds of impedances. Now what I can see over here is that this transmission line is connected to the analyzer over here. So that would mean this is the load position. This is the source and this is the load. Now there is nothing connected right now. So that means this is behaving like an open circuit load. So as you know, as per the impedance transformation relationship, whenever there is an open circuit load, as a function of the distance, the impedance keeps changing between open and short. So what you can see is that this green line is very close to the outer boundary of the Smith chart. But what you can see is that it is not exactly a circle, rather it is behaving in a spiral way. So just by looking at this, we can say that this line has some small loss characteristics. That means, as is practically more available, this is not a completely lossless line, but it is something like a low loss line. Alright, so let us now see more into this instrument. So this instrument currently is showing you the reading from 100 megahertz to about 1 gigahertz. So just to show you, let us put a marker. So right now marker 1 is at 100 megahertz. It is showing you the resistance as well as the reactance. It is roughly about 700 milliohms, the resistance part, and the reactance is about minus 103 ohms. So that's really high. So therefore the first step let us do is to measure the characteristic impedance of this transmission line. So to do that, I am going to have to terminate this transmission line using first an open load followed by a short load. So you can see this is open. So let me connect it over here. So you would not expect much of a change. So therefore let us note down this reading as ZOC. So ZOC at 100 megahertz is 1.1 minus J 99 ohms. Now let us replace this open load with a short circuit load. So as you can see, the point which was earlier over here has shifted diametrically opposite, as we expect, because open and shorts are converses of each other. So over here the ZSC is now about 1.13 ohms plus J 25 ohms. This is the reading at 100 megahertz. Now for the beta measurement, you will need to look at those points where the open or the short circuit impedance sort of repeats. So what you can see is that at 100 megahertz we are at this point. So let us see one more frequency where this same impedance point is repeating. So now I am moving. You can see the marker is moving and I am now coming back to the same point for a different frequency. So roughly it is about here. So at 769 megahertz, it is the point after 100 megahertz at which the impedance is repeating. So if I say F1 is 100 megahertz, then F2 is 769 megahertz, and these are impedance repeat frequencies. So as you remember, to measure the beta, we need to remove the phase ambiguity. So therefore, we are actually doing this measurement at two different frequencies. Now, before we actually go for the calculation, there is one small thing which we have to measure, and that is the length of the line. So the length of the line is essentially the length of this connector, which is roughly about 15 centimeters. This is my scale. So I can say the length is roughly about 15 centimeters. There may be a small error over here, but that is not very important. So with this, we shall now go for the calculations. So now that we have got the values, let us take these measured values and try to calculate what is the Z0. So Z0, as you know, is the geometric mean of the ZOC times the ZSC. So I have my calculator here with me. So let us punch in those values. So we have got a big complex number, which is something of this kind, 2476 minus J 84.37. So to get the root of this, let us convert this into the polar form. So that is 2477 with an angle of minus 1.95 degrees. So to get this is the quantity whose root we want. So therefore the Z0 will be nothing but root of 2477, that is 49.76 times roughly half of this angle, that is about 0.98. So this is what it is. So you can see that the Z0 is very, very close to 50 ohms with a very small alpha. This is something you can see. So if I now check this, what you will get is that when you are taking the root of this quantity, you have to check very closely which root you have to take, because there are two possible solutions even if you are taking the root of this number. So that will tell you the value of alpha. So for this, you need to choose the root where the real part of the Z0 is much larger than the imaginary part. So therefore, if you look at the whole complex number, that would be roughly about 49.75 minus J 0.85 ohms. So as you can see that it is mostly real with a very, very small imaginary component. So therefore we can say it is, for all practical purposes, a kind of lossless line. So now you can use these values and the proper length to obtain the values of alpha and beta, which I leave it to you for an exercise. Thank you. So this is a very simple setup of something called a slotted line. Now what you can see over here is that this is the front view of this slotted line section, which consists of a waveguide transmission line and which is terminated by a load. The load you cannot see right now because it is on the other side over here, but we shall be able to see it shortly. Now what you can see is this transmission line as part of the slotted line is actually made up of a rectangular waveguide. So if you take a scale and measure its A and B, that is the horizontal and vertical dimensions, you will see that this is roughly about 2.286 centimeter by 1.016 centimeter. If you are not able to remember these dimensions in centimeter, it's very simple. Just remember these dimensions in inches. This is about 0.9 inches and this is about 0.4 inch. So the dimensions of this waveguide are designed in such a way that the dominant mode of this rectangular waveguide, which is the TE10 mode, is able to propagate with a cutoff frequency that is in the range of about 6.5 gigahertz. So any wave which wants to travel in the TE10 mode must be given into this waveguide with a frequency above the cutoff frequency, which in this case is 6.5 roughly gigahertz. You can calculate the exact one yourself. Now this setup is primarily to cater for the X-band frequencies. Now X-band is a IEEE designated term which covers all the electromagnetic frequencies from 8.2 gigahertz to roughly about 12.4 gigahertz. Now let us see the top view of this. So this is the top view of this slotted line. Now you can see there is a small scale over here. This scale is holding a movable probe, which is this one, where you can mount something like a power detector or a voltage probe. And this scale, what you can see, is essentially a vernier scale, which allows you to measure the distance from here, that is the distance from the load, that is the quantity L in case of transmission lines. If you notice very closely, there is a slot on the waveguide, that's why it's called a slotted waveguide line, which allows you, or which allows this voltage probe to penetrate into this waveguide. Therefore, it can get an idea of the surface current or the fields that are generated inside. And you can see that the impedance characteristics or the maxima, minima, they will repeat after every lambda by 4. So although we will not show this exact behavior right now, what you will know that this is the place where you will connect the source and the load is over here on the other side. And this is using a voltage probe. You can connect an oscilloscope, you can connect a power detector, and by changing the position of this tunable movable probe, you can do a lot of measurements. So that we will do some other time. Now we shall see a very simple experimental demonstration of the magic of polarization. Now polarization, this effects in practice, I shall be explaining to you using this huge setup that you can see around me. Now I will explain this setup to you very briefly. This is an antenna. This is also an antenna. Now you can see that this antenna is made up of a big metallic object, whereas this antenna is simply consisting of two black colored rods and a black cubical structure in the middle. So structure wise, these two antennas are very different. Now even though these antennas are very different, the common fact about them, both of these antennas, is that they can transmit and receive linearly polarized signals. To be specific, these two can receive vertically polarized signals. Now what that means is, if this is the transmitting antenna and a wave is traveling from the transmitter antenna to the receiving antenna, then its electric field vector would be aligned vertically, just the way this is. The receiving antenna is oriented. Now let us look at the transmitter setup. This big piece of equipment is an RF signal generator. So what I have now configured this, I have configured this equipment to generate an electromagnetic wave of frequency 1.4 gigahertz with an amplitude of 10 dBm. Now what is dBm? dBm means power level with respect to 1 milliwatt of power. So therefore, if you use the logarithmic scale, 10 dBm would correspond to 10 milliwatts of power. So what is essentially going to happen is that this 10 milliwatts of power will be fed to this transmitting antenna, and this power would essentially reduce in magnitude as it goes to the receiver. With this, let us look at the receiver setup. So this is the receiver now. This antenna, which is black in color, is what is called as a simple dipole antenna. This antenna, since it is receiving the signal, or it is trying to receive the signal, is connected to this piece of equipment called a spectrum analyzer. Now this spectrum analyzer has a very interesting property, is that it can show you the frequency components of the signal that we are going to receive. Now right now what you can see is that it is nothing but noise. There is just a lot of noise over here because there is no signal in the ambient around us. And in particular, we are looking at the frequency range from 1 GHz to 1.8 GHz. So that means around us at this point of time, there is no signal which this antenna is receiving. Now you may ask, why is this signal, or why is this instrument or the antenna not receiving the 1.4 GHz wave that we are transmitting? Well, it's a simple thing. We are not receiving anything because even though we have configured the transmitter, we have not yet switched on the signal. So therefore, let us switch it on. Now I am switching on the signal. Let us see what magic happens. You can clearly see that there is a nice spike over here. This indicates that the receiving antenna is receiving a signal of strength minus 17 dBm. Now look at the difference. We have transmitted plus 10 dBm from the transmitter, and the receiver, which is barely a meter or two away from the transmitter, is receiving a very weak signal of minus 17, minus 18 dB. Now let us do a very small thing. Let us change the orientation of the receiver antenna. I am going to now rotate this by 90 degrees so that the orientation of this receiving antenna will make it receive only horizontally polarized signals. So now I have made it almost 90 degrees. Now if you look at the signal strength which it is receiving, it has become much more weak. It is almost of the order of minus 36 dBm, and earlier it was minus 18 dBm. So this is what we mean by non-matched states of polarization. So the transmitter antenna is vertically polarized and the receiving antenna is now horizontally polarized. So therefore the transmission and reception efficiency is not being maintained. This is what polarization, the role it plays in modern day wireless communications.
The window that you are seeing in front of you is that of a commercially available simulator, and that is the AWR design environment provided by National Instruments. IIT Bhubaneswar has licenses for this software which can be used to design a number of systems using electromagnetic waves, and in particular radio frequency and microwaves. So today let us see some effects or rather some phenomena using transmission lines and waveguides that we have learnt in theory so far, but perhaps it may so happen that the practical insight may not be 100% clear. So let's do that. So let me open a project which I already have, and that is a quarter wave transformer. So a quarter wave transformer, as you know, is nothing but a transmission line which is used to match a real load with some transmission line with real characteristic impedance. So here what you can see, I have a load resistance of value 100 ohms, and here I have placed a port of value 50 ohms. So this essentially means that it is very equivalent to a transmission line with characteristic impedance 50 ohms. Now when I connect this 50 ohm line directly to the 100 ohm load, definitely there will be some reflection. Now to stop that reflection, we have to put in a piece of transmission line in the middle between the main line and the load, and that is nothing but the quarter wave transformer. So let us see what the reflection actually looks like if this were to be a 50 ohm line. So here I have changed the Z to 50, which means that this transmission line has impedance 50 ohms. This 90-degree means it is lambda by 4, that is the theta or the beta L of the line, and this becomes equal to lambda by 4 for a given frequency of 1 gigahertz. So now this entire setup has essentially become very much like a transmission line of 50 ohm impedance feeding a 100 ohm load. So therefore, let us simulate this and see what happens. What we are essentially looking for is the reflection coefficient seen by the transmission line at the load. So essentially what is happening is something like this. So this is the simulate option. So it's ready. Let us see the graph. Yes, what you can see is this parameter, what I'm calling as S11, essentially indicates the ratio of the output wave to the input wave, both at port 1, which essentially signifies the reflection coefficient magnitude. So that is roughly about 1/3, and that is what we expect because the ZL is 100 ohms and Z0 is 50 ohms. Now what we will do is we shall put a quarter wave transformer whose characteristic impedance is exactly equal to the geometric mean of the line impedance and the load impedance. So therefore, the impedance of this middle line, that is the quarter wave line, must be the root of 5000, or that is 70.71 ohms. So once I do this and I simulate, what should happen? When the frequency becomes equal to 1 gigahertz, at that time, this quarter wave will provide the best possible matching. And at that point, the gamma must be equal to 0. So let's see if that works. Simulation complete. Yes, you see at 1 gigahertz, the gamma is going to 0. And when you increase the frequency, a similar phenomena happens at 3 gigahertz. So this tells you that a lambda by 4 quarter wave transformer will also provide you good matching at the odd harmonics of the frequency as well. Now what you can see is that the value of gamma is, let us say, below 0.1 for a very narrow range. Let us see what that range is. So I'll just add a marker over here. So what you can see is that from roughly about 809 megahertz to about 1.2 gigahertz, so that is roughly about 400 megahertz. It's giving you the bandwidth, or it's giving you the value of gamma that is below 0.1 for this frequency range. So generally, depending on what kind of application you're looking at, this is rather narrow. So now that is one drawback of the quarter wave transformer which we have discussed in the class, that its bandwidth over which it can provide you good matching is very, very low, obviously because its size is dictated by the frequency. Now let us look at one step higher, that is a quarter wave transformer but with two sections. So let's open this. So now let's see what I'm trying to do. I am trying to do the same problem wherein I have to match a 100 ohm load to a 50 ohm line. But now instead of using one quarter wave line, I am using two lines, each of lambda by 4. As you can see, the line 1 is 90 degrees, the line 2 is also 90 degrees. So, but then what is happening is the impedance or the characteristic impedance I have calculated for each of these lines is not 70.71. Essentially, they're calculated in a different way. Now, how they're calculated, I shall not tell you that right now. So what you can see is that the values definitely of the characteristic impedance of these two lines are something between 50 ohm and 100 ohm. That is between Z0 and the ZL. But that does not mean you can choose any value. There is a way to analyze this. The analysis of these impedances can be done if you take some advanced level course on microwave and RF design. So let us simulate this. and try to measure the reflection coefficient that is seen by the main line. And here we go. You can see that the gamma value, the mod of gamma, is very close to 0 for a very large range of frequencies. So if you now put another marker, we can see earlier the bandwidth was from 800 megahertz to about 1.2 gigahertz. So here let's see what it is. It is now from 623 megahertz to about 1.384 gigahertz, so which is much more than what we had got in case of a single section quarter wave transformer. Now, using this approach, we can continue to increase the number of sections. So just for the sake of completion, let us go for one more. That is a quarter wave, but with 3 sections. So now again, the problem is the same. The load is a 100 ohm load and the line is a 50 ohm line. So here I have put 3 quarter wave transformers of impedances again, which are between the Z0 and ZL, but which are not any random values, but they are calculated with some specific technique. So one is, the first impedance is 54.34 ohms, the second impedance is 69, and the third impedance is 89.5. So we expect that as we add more and more number of sections of quarter waves with predetermined impedances, the bandwidth of matching should increase. So if I simulate this, what I will observe is, as you can see, the bandwidth has increased even more. So let us see what it is now. So here we are having a bandwidth from almost 500 megahertz to almost 1.5 gigahertz. So it is much higher than the earlier 2 cases. So therefore, if you want broader bandwidth for matching, you need to increase the number of sections. But the drawback of that is that each section is lambda by 4 in length, and therefore what happens is that these lines will consume a lot more of additional area. So there is a lot of research going on how to make compact impedance matching sections, which are also able to provide you very high matching bandwidths. Now let us look at one more example, and that is a rectangular waveguide. So when I have the rectangular waveguide, as you know, there are the concept of modes in waveguides. So what I have done essentially is that I have fed this waveguide, which has dimensions of 2.28 centimeters by 1.01 centimeters. It is very same, or it is exactly the same as the waveguide that I have shown you in the lab in the earlier part of this video, and I have taken the length of this waveguide as 100 millimeters. So that is the length of the effective transmission line. So if I were to use this waveguide as a transmission line, the length of the transmission line would be about 10 centimeters. And the mode that I'm using is the TE mode. This is the dominant mode which I want to use. So depending on which mode I'm exciting, I can change the values of M and N. And since it is an air-filled waveguide, the epsilon inside the waveguide is 1. So now let us try to see, if I am feeding some signal on one end, what is the signal I'm receiving at the other end, but as a function of frequency. So therefore, let's simulate this. Great. So now I am going to see the magnitude of the transmission coefficient. That is, if you have an input at port 1, what is the output at port 2? So now you can see that there are many of these local maximas which you are getting. Now what are these? Let's see. Let us look at the smallest or the earliest minima. So let's place a marker over here. So what I'm getting is 6.73 gigahertz. There is a peak over here. Now, as you know, the dominant mode is that mode which is able to provide you the lowest cutoff frequency. And what you will see is that this 6.73 is very, very close to the cutoff frequency of the TE10 mode. And that is why this has the lowest frequency. Now, if you go higher, you get something like 7.21 gigahertz. It may be the cutoff frequency of some higher mode, for example, TE20 or TE11. We don't know what it is. So you can simply substitute the values of M and N and get this. So there is another peak at 7.95. There is one more peak at 8.89, so on and so forth. This is what we mean by the modes of a waveguide. There are multiple maximas which get transmitted more easily. Now, if I were to input some signal which is a non-sinusoidal wave, let us say I am feeding one wave whose base frequency is 6.73 gigahertz. And there is also one more signal component which is at 7.21 gigahertz. Now, let us see how the dispersion actually happens. So one is 6.7 gigahertz, the other is 7.21 gigahertz. For a dispersion-free transmission, the system should have a linear phase response. So if you look at the phase response of this, you can see clearly that the phase response at the different frequencies is not linear. So there may be some local linearity, yes, but overall the phase response is not very linear. So there is definitely some kind of a disturbance or discontinuity in phase over here. So if I now look at, if I place a marker at 6.7 gigahertz, that's somewhere over here. So 6.7, the marker is around 154 degrees, that's the phase. And at 7.2, it's about minus 41. So clearly between 6.7 and 7.2, the phase relationship, as you can see here, is definitely not linear. So therefore, there will definitely be some delay in the frequency components. And as we discussed, that if there are multiple frequencies which are traveling as part of the same signal, the signal that you obtain at the output will definitely not be of the same wave shape which was given as the input. So definitely there will be some kind of a dispersive effect, and this is what I wanted to show you. Let us now take a look at the behavior of transmission lines, but from a time domain perspective. That means how transmission lines behave as a function of time. Now, it is not very easy to visualize that, but I shall try my best to show you how to do a simple experiment to visualize that to some extent. Now, the window that you see in front of you is nothing but LT-Spice. It is a SPICE-based program, and it is available free of cost. And it is just, it's very similar to ngSpice, but with a user interface. So let's get to business. Let's make a new schematic and add an element called as T-line. Now this stands for transmission line. So this is what we get. Now what this means is Z0 is something that you know. That means the characteristic impedance of the line is 50 ohms. TD equal to 50N means the propagation time of the wave from one end to the other end. That means if an electromagnetic wave is traveling across the length of the transmission line, it will take roughly about 50 nanoseconds to do the to cover this distance. So let us change this a bit. Let us change this properties a little bit. Let's make it as 5 nanoseconds. So now we have a 50 ohm lossless line, and the wave traveling from one end to the other end of the line takes 5 nanoseconds. So therefore, let us introduce a voltage source. And let us say that this voltage source is a sine wave with the following parameters. DC offset is 0, 1 volt amplitude, a frequency of 1 gigahertz, which would make the time period of this wave as equal to 1 nanoseconds. Delay is 0, phase is 0, and let us have 100 cycles. So there we go. And let us now introduce a load. Let us put a load resistance which is not equal to the characteristic impedance. So if the characteristic impedance is 50 ohms, let us introduce a load of 100 ohms. Now let us complete the connections. This is what the circuit will look like. Let us now connect a ground, because every circuit needs a ground. So there we go. Now let us do a transient analysis. So in the transient analysis, let us say I want to stop this at 100 nanoseconds, and the time which I want to look at, the start time, is 0, and let me specify a time step of 0.02 nanoseconds. And yeah, let's be ready with this. So now let me see what is the voltage across the load. So the moment I put the marker across the load, this is what I see. Now you observe something very interesting. For the first 5 nanoseconds, this is a plot of voltage versus time. For the first 5 nanoseconds, there is nothing across the load. Why? Because the wave takes a minimum of 5 nanoseconds to travel from the source to the load. So therefore, obviously, you will see nothing at the source side. But at 5 nanoseconds, just after 5 nanoseconds, the wave hits the load and starts to undergo reflection. Now the reflection coefficient is something that you can easily calculate, that is ZL minus Z0 by ZL plus Z0. So what we are seeing actually, after 5 nanoseconds until about 15 nanoseconds, it is the superimposed voltage that is arriving as a result of two waves. One is the forward wave, the other is the reverse wave. So if the forward wave has an amplitude of 1 volt, then the reverse wave will have an amplitude that is equal to gamma L times 1 volt. Now what is gamma L? Gamma L is 100 minus 50 divided by 100 plus 50, that is 1 by 3. So 1 plus 1 by 3 is roughly about 1.33. So if you look at the marker, you will see that the voltage is roughly about 1.32 or 33 volts. So what is essentially happening is that this point onwards, you are having superposition of two waves. One is the forward wave, the other is the backward wave. Now once it starts traveling, it will take another 5 nanoseconds to travel back and then hit the source. So when the backward wave comes back to the source, what will happen? The impedance of the source is 0. So therefore this whole wave will be reflected back and it will take another 5 nanoseconds to come to the load. So the change at the load will start happening from 50 nanoseconds onwards, because one round trip from back, so load to source and again source to load. So then what happens is you are having this short circuit load. This short circuit load will reflect the entire reflected wave back towards the load with a reflection coefficient of -1. So therefore, after 50 nanoseconds, the amplitude of the load voltage again dies down. So you can see these changes happen many times. So you have high voltage, then low voltage, again little high, again little low, again little high, and after a point of time, it seems to settle down. So what happens is, what the voltage you observe across the load or at any point across the line is essentially a function of time, and it is steady state. So it is caused essentially not by one set of reflections, but by multiple sets of reflections. And if you look at some long time after 0, let us say 100 nanoseconds, you will see that the magnitude of this voltage is very, very, very close to 1 volt. What this means is, because there is no source resistance and the transmission line is lossless, the wave is sent from the source to the load without any loss. But there are reflections. So that is why you will always see that there is the voltage across the load is not exactly equal to 1 volt, but it's something very, very close. So after a point of time, you will definitely get 1 volt, but always there will be some reflection in terms of energy. Now let us do a very simple change to this circuit. Let us put a source resistance. Let us introduce a source resistance of value, let's put 100 ohms. Let's say the value is 100 ohms. So let's connect this. Now how will this setup behave? Let us see that. So now let us again see the load voltage. Now you see something very interesting. Now you see that obviously there are some ups and downs in the load voltage, but it is different from what it was before, because now we have introduced a source resistance. So the first time the reflected wave goes back to the source, it will again undergo one reflection with a reflection coefficient of 1 by 3. So that will keep getting added up, and the resultant voltage magnitude will be roughly about 500 millivolts, which you see is exactly equal to half of the amplitude of the input voltage. Now, what this shows us is that it is as if the transmission line is not playing any role except providing some delay. So this 100 ohm resistor and this load 100 ohm resistor, they are acting like a voltage divider after some point of time. So this 1 volt will come as 0.5 volts or 500 millivolts across the load. This is what you see as the beauty of the transmission line. There is no way to see the two different waves which are flowing. What you will essentially see is always the superposition of the two waves. And that is what I wanted to show you in this part of the video.